Right now, at the altitude where commercial aircraft cruise and where weather, as we have understood it for the entire history of organized meteorology, is supposed to live. Something is happening that the operational forecast models did not predict, that the climate models did not cleanly anticipate on this timeline, and that the people who spend their entire careers staring at upper air charts are quietly describing in private channels as a configuration they have never seen in their working lifetimes. The 50 hectopascal level, that is the stratosphere, roughly 20 kilometers above your head, roughly 65,000 feet, well above where any storm you have ever experienced was born, is registering temperature and zonal wind anomalies that, when overlaid against the 75-year reanalysis record, do not just sit at the tail of the distribution. They sit beyond it. They sit in a region of the probability space that, until this month, was effectively empty. Let me say that again so it registers. The atmosphere has produced a value that, in 3/4 of a century of continuous observation, has no analog. Not a close one, not a comparable one, no analog at all. And the people whose job it is to translate stratospheric behavior into surface consequences. The ones who write the products that determine whether your county gets a winter storm warning, whether your airline reroutes a polar flight, whether your grid operator prepositions reserves, are now in the position of having to forecast downstream from a state of the system that has never been benchmarked. They are flying in the most literal operational sense without a map. This is not hyperbole. This is the language being used in the technical discussions out of the Climate Prediction Center, out of the European Center for Medium-Range Weather Forecasts, out of the polar vortex research community that has been tracking sudden stratospheric warming events since the 1950s. The phrasing, and I am paraphrasing the operational tone here, not inventing it, is that the ensemble spread has collapsed onto a solution that the historical climatology cannot validate, because the historical climatology contains nothing like it. If this has you hooked, subscribe to the SkyAb so you don't miss what comes next, because this story is just getting started. And what is happening in the upper atmosphere right now is going to be reshaping surface weather, jet stream geometry, and extreme event probability across the entire northern hemisphere for weeks, possibly months. Drop a comment below. I want to know where in the world you are watching from, what time it is where you are, and your honest take on this question. When the atmosphere does something nobody alive has ever seen, do you trust the models that are forecasting what happens next? Or do you trust the humans interpreting models that were trained on a climate that no longer exists? I want to walk you through this carefully because the framing matters. This is not a story about one storm. This is not a story about one cold snap or one heat wave or one freak event you'll see on the local news for 48 hours and then forget. This is a story about the machinery, the actual physical machinery, of how weather gets made on this planet. And the machinery has just produced an output that, by the standards of every model we use to anticipate the future, should not be there. The thesis of this video, stated as plainly as I can state it, is this: the atmosphere is not malfunctioning. It is functioning exactly as physics demands it function given the energy that has been added to it. The reason it looks like a malfunction, the reason every chart you are about to see has a color scale that runs off the edge, is because the assumptions we built into our intuition about what the atmosphere can do were assumptions about a smaller energy budget. That budget has been revised, and the revisions are showing up not as gentle warmings or polite shifts, but as configurations that break the historical envelope entirely. This is not a malfunction. It is a math problem, and the math has changed. Let me put that in a framework that actually means something. The stratosphere, the layer of the atmosphere that sits above the troposphere where all your weather happens, has, for as long as we have had instruments capable of measuring it, behaved in a way that is, broadly speaking, predictable. There is a polar vortex that strengthens in winter as the pole goes dark and cools radiatively. There is a tropical stratospheric oscillation, the QBO, the quasi-biennial oscillation, that flips its zonal wind direction roughly every 28 months. There are sudden stratospheric warming events, SSWs, which occur on average about 6 times per decade, and which can dramatically reconfigure the polar vortex and propagate consequences down into the troposphere over the following 2 to 6 weeks. This is the textbook. This is what every operational meteorologist learned in graduate school. This is what the Climate Prediction Center's stratosphere page is set up to monitor. What happened, beginning roughly 3 weeks ago and accelerating through the most recent analysis cycles, is something that does not fit any of those categories cleanly. It is not a classical major sudden stratospheric warming, though it has features of one. It is not a clean QBO phase transition, though the QBO is doing something itself that is anomalous. It is not a textbook minor warming. It is a configuration in which the temperature anomaly at 10 hectopascals, that is roughly 30 kilometers up, well into the middle stratosphere, has departed from the 1991 to 2020 climatological mean by a magnitude that, when expressed in standard deviations, lands in territory that the reanalysis record does not contain. I want to give you the actual number. The anomaly being reported in the most recent assimilation cycles from the ECMWF reanalysis and corroborated by the NASA MERRA2 product is on the order of 5 standard deviations above the climatological mean for this date. 5 standard deviations. Let that number breathe for a second. In a normal distribution, and stratospheric temperature anomalies are not perfectly normal, but they are normal adjacent enough for this framing to be useful. A 5 sigma event has a probability of occurring on any given day of roughly 1 in 3. 5 million, that is not a colloquial rare. That is a number that, if the underlying distribution were truly stationary, you would expect to see approximately once every 10,000 years. It is happening this week. And before anyone in the comments points out correctly that the underlying distribution is not stationary, that we are in a warming climate and the distribution itself is shifting, yes, exactly. That is the entire point. The 5 sigma framing is what the historical baseline tells us. The fact that the event is happening tells us the historical baseline is no longer the relevant baseline. This is the key thing that separates this event from any prior stratospheric anomaly in the satellite era. We have had major sudden stratospheric warmings before. The 2009 event, the 2018 event, the 2021 event that contributed to the February Texas freeze. Those were significant. Those reconfigured the polar vortex. Those propagated into surface weather. But those sat within the historical envelope. You could find analogs. You could pull a 1985 case, a 1957 case, a 2013 case and overlay them. And the operational forecasters could say, with reasonable confidence, here is what tends to follow. This event does not have analogs. The compositing exercise that operational centers run, where they take the current state, find the closest historical matches, and use those to build a downstream forecast. That exercise is producing, in the current cycle, a flat distribution. There is no nearest neighbor. There is no closest match. The state space the atmosphere has entered is, with respect to the reanalysis record, empty. That is what the forecasters mean when they say, quietly in the technical discussions, that they are flying without a map. Here is the part that most people never heard about, and that the mainstream coverage of this event, to the limited extent it has covered it at all, has either glossed over or gotten wrong. The stratosphere is not weather. The stratosphere is the upstairs neighbor of weather, and the upstairs neighbor, when it rearranges the furniture, vibrates the entire building. The mechanism by which stratospheric anomalies translate into surface consequences is called downward propagation, and it works, in simplified terms, like this. When the polar vortex, the band of strong westerly winds that circles the pole in the stratosphere during winter, gets disrupted, weakened, displaced, or split, the disruption propagates downward through the atmosphere over a timescale of roughly 2 to 6 weeks. As the disruption descends into the upper troposphere, it changes the geometry of the jet stream. The jet stream, instead of being a tight, fast, zonal flow circling the hemisphere, becomes wavier, slower, and more meridional, more north-south rather than west-east. A wavier jet stream means that the ridges and troughs that drive surface weather, the high-pressure areas and the low-pressure areas, get larger in amplitude and slower in forward motion. Cold air from the polar regions plunges further south. Warm air from the subtropics surges further north. And whatever weather pattern sets up tends to lock in for longer, because the slow-moving wavy jet does not flush it out the way a tight zonal jet would. This is the mechanism behind almost every winter cold air outbreak of the last 15 years that you have read about in the news. The 2014 polar vortex event, the 2021 Texas freeze, the 2022 Christmas cold snap in the eastern United States, the series of cold snap and snow events that hammered northern Europe in February 2018 and again in early 2021. Every one of those was, to a first approximation, a downstream consequence of stratospheric disruption that had occurred 2 to 6 weeks earlier. The reason the people who watch the stratosphere are calm-voiced but not casual right now is that the disruption currently underway is larger, by the standard metrics, than any of those. The polar vortex is not just weakened. It is, in the most recent analyses, structurally compromised in a way that suggests we are headed not just for a single cold air outbreak, but for an extended period, possibly 6 to 10 weeks, of a fundamentally reorganized hemispheric flow pattern. 6 to 10 weeks, across the entire northern hemisphere. Let me put that in terms of what it actually means for the people watching this video. If you live in the central or eastern United States, this raises the probability, and I am being careful to say probability, not certainty, of multiple extended cold air outbreaks between now and the early part of next year. If you live in the United Kingdom, in Ireland, in northern France, in the Low Countries, in Scandinavia, this raises the probability of blocking patterns that pull cold continental air westward, across an island geography that is not built for it. If you live in East Asia, Japan, Korea, northern China, this raises the probability of intensified Siberian outbreaks pushed south by a meridional jet. If you live in the Mediterranean, this raises the probability of extended dry, mild stretches, punctuated by sudden, severe storm intrusions when the wavy jet finally does break a ridge. And if you live in the subtropics or the tropics, and you are wondering why you should care about a polar vortex disruption, the answer is that the redistribution of mass and momentum in the upper atmosphere following a major stratospheric event does not respect latitude bands. Tropical convection patterns get modulated. The Madden-Julian oscillation, the MJO, which controls the eastward propagation of tropical rainfall on a 30 to 60-day timescale, responds to upper-level forcing in ways that are still being researched, but that show up clearly in the case studies of past SSWs. Hurricane seasons, monsoon timing, drought breaks, drought entrenchments, All of them are downstream in some statistical sense of what the upper atmosphere is doing right now. This is not theory. This is thermodynamics. This is the energy budget of a coupled fluid system that has just had a major reconfiguration in its highest dynamically active layer. The explanation is complete. The atmosphere is one system. What happens at 30 kilometers does not stay at 30 kilometers. I want to spend some time here, because this is the part that is going to determine whether you can recognize, in the coming weeks, whether the narrative being constructed around this event in the media is accurate, or whether it is being flattened into something simpler and less true. A textbook sudden stratospheric warming has a recognizable signature. The temperature at 10 hectopascals over the polar cap rises rapidly, often by more than 25 degrees Celsius in a few days, sometimes by 40 or 50 degrees Celsius in the most extreme cases. The zonal mean zonal wind at 60 degrees north latitude and 10 hectopascals reverses from westerly to easterly. The polar vortex either displaces, meaning the center of the cold core wobbles off the pole, often toward Eurasia or toward North America, or it splits, meaning the single vortex breaks into two daughter vortices, each of which then evolves on its own. These are the operational definitions. The World Meteorological Organization has codified them. The research community has built decades of analysis on top of them. When a SSW happens, the diagnostics are run, the event is classified, and the historical compositing begins. The current event satisfies some of these criteria and violates others in a way that has not been observed before in the reanalysis era. The polar cap temperature has risen, yes, but not in the classic spike and recover pattern. It has risen and stayed elevated, with a secondary intensification that the climatology does not contain. The zonal wind at 60 degrees north and 10 hectopascals has reversed, yes, but the reversal extends both higher and lower in the atmosphere than the classical pattern, suggesting that the wave forcing driving the event is not the canonical wave number 1 or wave number 2 pattern that drives most observed SSWs. There are indications, and I am being careful here because this is at the edge of the published research, that wave number 3 forcing, which is much rarer, is playing a role. If wave number 3 forcing is in fact contributing significantly to this event, that has implications that the operational forecast guidance is not equipped to handle. Wave number 3 SSW-like events have appeared in idealized model studies. Scaife and colleagues at the UK Met Office have published on the broader question of how unusual planetary wave configurations propagate. But the case study library of real wave number 3 forced events is, to put it charitably, thin. We have a handful of suspected cases in the satellite era, none of them at the magnitude currently being observed. The polar vortex itself, to the extent we can speak of the vortex when its structure is in active reorganization, is in a configuration that is best described as displaced and partially split. There is a primary cold core remnant that has migrated off the pole and is currently centered over a region that, depending on which analysis you trust, lies somewhere between Greenland and the Norwegian Sea. There is a secondary cold core feature, smaller and less coherent, over central Siberia. The classical question, is this a split event or a displacement event, does not have a clean answer this time. It is both, simultaneously, and the literature on hybrid events is sparse. This matters because the downstream consequences of a split SSW and a displaced SSW are statistically different. Displaced events tend to favor cold air outbreaks in one region. Split events tend to favor cold air outbreaks in two regions, sometimes simultaneously, sometimes sequentially. A hybrid event of the magnitude being observed could, in principle, drive cold air anomalies across 3 or 4 distinct regions of the hemisphere in overlapping windows. Here is the part that should stop you cold. The model ensemble guidance for downstream surface impacts. The actual operational product that goes into the seasonal outlooks at the Climate Prediction Center, at ECMWF, at the UK Met Office, at the Japan Meteorological Agency, is, in the current cycle, showing a spread that is wider than the spread typically associated with a strong El Niño or a strong La Niña teleconnection. The ensemble cannot agree, not because the models are broken, but because the initial condition state is so far outside the training data that small differences in model physics produce large differences in evolution. This is what it looks like when the atmosphere does something the models were not built to anticipate. The models do not refuse to produce a forecast. They produce many forecasts, and the forecasts disagree. Because the underlying system has entered a region of state space, the model developers never weighted heavily during training. The forecast is not wrong. The forecast is honest. The honesty is that we do not know, with the precision we are used to, what comes next. And the people who do this for a living, the operational stratosphere watchers at the Climate Prediction Center, the polar vortex specialists at the Alfred Wegener Institute, the SSW researchers at the University of Reading, the ensemble forecasters at ECMWF, are saying so out loud in technical discussions with a frequency and a tone that, if you have followed this field for any length of time, is itself the signal. When the experts stop hedging and start saying, "We have not seen this before," the appropriate response is not panic. It is attention. Focused, sustained, technically literate attention. That is what this video is for. When something in the atmosphere appears to break the chart, the first instinct inside every forecast center is the correct instinct. Go find analogs. Go find the years that rhyme. Go find the events that looked strange at the time, because the atmosphere has a way of surprising each generation in its own dialect. And the fastest way to avoid overstating novelty is to ask whether the novelty is actually memory failure. So people started reaching for the familiar names. They reached for 1952 because that winter contained one of the earliest documented major stratospheric warmings in the modern record. They reached for 1985 because the January cold outbreak over North America remains one of the signature examples of hemispheric blocking tied to an upper-level reorganization. They reached for 2009 because that was a textbook major sudden stratospheric warming with a dramatic vortex split. They reached for 2018 because Europe remembers the beast from the east and forecasters remember how clearly the stratospheric precursor showed up. They reached for February 2021 because the Texas freeze has become, for a lot of people, the public shorthand for what happens when the polar vortex breaks. And here is what happened when those analogs were overlaid. They helped for about 5 minutes, then they failed. The 1952 event was large, yes, but the observing network at the time was sparse. The vertical resolution was limited. And the reanalysis uncertainty on upper-level structure is wide enough that trying to use it as a one-to-one analog for a modern event is more an act of historical humility than operational utility. The 1985 case gives you downstream tropospheric consequences, but it does not give you a clean stratospheric structural match. The 2009 event gives you a vortex split, but not this persistence profile. The 2018 event gives you a major warming, but not this amplitude in the warm anomaly, and not this hybrid displaced and split geometry. The 2021 case gives you a strong downstream cold signal, but again, not the same precursor state. This is the pattern. Every precedent gives you one piece and fails on the other 3. That matters more than people realize, because historical analogy is not just an intellectual comfort blanket for meteorologists. It is operationally useful. If you have a clean analog set, you can say with some confidence that when the stratosphere looked like this, the surface tended to look like that. When the analog set falls apart, you do not merely lose certainty. You lose the ability to communicate probability in a way the public is used to hearing. Let me say that again so it registers. This is not simply a case where the atmosphere is doing something severe. It is a case where the usual method for translating severity into confidence has broken down. That is why this event feels different even to people who have lived through other unusual winters. It is not just the anomaly itself. It is the absence of a map from anomaly to outcome. And there is another layer here that is more unsettling. Some of the analogs fail, not because the stratosphere has never done anything comparably strange, but because the background climate state underneath, the stratosphere, is no longer what it was when those earlier events occurred. A sudden stratospheric warming in 1985 descended into a troposphere with a different sea surface temperature distribution, different Arctic sea ice coverage, different soil moisture patterns across Eurasia and North America, different baseline ocean heat content, and different mean geopotential thickness over the continents. In other words, even if the stratospheric event were identical, and it is not, the surface canvas it is descending into would not be. That is the hidden problem with analog forecasting in a warming climate. The upstairs event might resemble something from the past. The downstairs house has been renovated while nobody was looking. A 2022 review in Nature Reviews Earth and Environment by Cohen and colleagues went into this general problem from the perspective of Arctic change and mid-latitude extremes. The teleconnections are not disappearing, but the background state they operate through is shifting, which means the old relationships can weaken, strengthen, or change sign depending on the season and the configuration. That sounds abstract. Operationally, it means you can have the same upper air trigger and get a different surface response because the baseline the trigger lands on has changed. Think of it like striking a bell. If you strike the same bell in the same way, you expect the same sound. But if someone has thickened the metal, warmed the room, changed the clapper and put the bell underwater up to the rim, the same strike does not produce the same note. The forcing can be similar. The response is not. That is where we are now. The atmosphere did not merely produce a rare stratospheric event. It produced a rare stratospheric event over a planet with warmer oceans, thinner ice, higher lower tropospheric moisture content, altered snow cover, altered land-atmosphere coupling, and a jet stream already under stress from latitudinal temperature gradient changes. So even if you think you have found a historical rhyme, you are still trying to forecast the second half of the sentence in a language whose grammar has changed. This is why phrases like "we've seen this before" can become actively misleading. No, we have seen pieces of this before. We have not seen this entire stack before. And when you are trying to understand risk, the stack is everything. Here is the part that most people never heard about because it is less cinematic than a tornado video and less politically useful than a culture war slogan. The atmosphere is not acting weird. It is acting richer, richer in energy, richer in moisture, richer in gradients where the gradients intensify motion, and flatter in gradients where the flattening slows motion. Richer in the raw ingredients that produce both persistence and violence. The most basic number in this entire story is not a wind speed and not a pressure anomaly. It is radiative forcing. Since the late 19th century, the Earth system has been accumulating energy because greenhouse gases have reduced the efficiency with which outgoing long-wave radiation escapes to space. The best estimate from the IPCC 6th Assessment Report is that Anthropogenic effective radiative forcing relative to 1750 is now well above 2 watts per square meter, once all relevant agents are combined, and carbon dioxide alone accounts for the dominant share of that positive forcing. 2 watts per square meter sounds small. It sounds like nothing. It sounds like the kind of number you could ignore. Do not ignore it. 2 watts per square meter averaged over the surface area of the Earth is an absurd amount of energy. Let me put that in a framework that actually means something. The surface area of Earth is about 510 million square kilometers. That is 510 trillion square meters. Multiply even a couple of watts by that many square meters, and you get a planetary energy imbalance on the order of 1 quadrillion watts. Roughly speaking, the Earth system is accumulating heat at a rate comparable to the energy release of several Hiroshima-sized bombs per second, every second, day and night, year after year. Different communicators use different analogies for this. The exact bomb count framing can vary depending on the baseline and the year. The important thing is not the metaphor. The important thing is that the number is enormous. Most of that extra heat goes into the ocean, more than 90% of it. That is why ocean heat content is one of the most important variables in climate science, and why papers by Cheng and colleagues, published repeatedly in venues like Advances in Atmospheric Sciences, have become central to the modern understanding of what global warming actually means in physical terms. It means the ocean is banking heat. It means the atmosphere is sitting on top of that bank. And it means the weather system, when it reaches for fuel, is increasingly reaching into a hotter reservoir. But some of that energy remains in the atmosphere and in the coupled land-atmosphere system. And when it does, it changes the range of what is dynamically possible. Warmer air can hold more water vapor. This is Clausius-Clapeyron, one of the cleanest relationships in atmospheric thermodynamics. Roughly 7% more water vapor per degree Celsius of warming, all else equal. That does not mean every storm rains 7% more for every degree. Real storms are more complicated than that. But it does mean the ceiling rises. The moisture reservoir grows, and when the dynamics line up, the precipitation can become extraordinary. At the same time, warmer oceans alter the placement and persistence of the ridges that steer the jet stream. Warmer polar region reduce the equator-to-pole temperature gradient in the lower troposphere in some seasons and regions, which can weaken the westerlies and encourage wave amplification. Meanwhile, warming in the tropical upper troposphere can alter gradients aloft in ways that do not produce a simple, single-sign outcome. This is why the literature on jet stream change is contentious in details, but not in stakes. The system is being perturbed in multiple places at once. And above all of this, the stratosphere, which many people still think of as a detached layer, is not exempt. It is connected to the changing troposphere below and the changing chemistry above. Ozone recovery modifies stratospheric temperature structure. Greenhouse gas increases cool much of the stratosphere radiatively even as they warm the troposphere below. Planetary wave forcing from the troposphere can intensify as the lower atmosphere reorganizes. The stratosphere is not a sealed room. It is a ceiling being pushed on from below and reconfigured from within. So when the atmosphere produces an event that seems to exceed the old climatological envelope, the first question should not be, how could this happen? The first question should be, given the added energy, the altered gradients, and the changed coupling between layers, why did we think the old envelope would continue to contain the system indefinitely? That is the rhetorical pivot. The anomaly is not the atmosphere. The anomaly is our expectation. We built intuition on 20th century baselines. We are living in 21st century forcing. The numbers do not just get worse, they break. And this is where a lot of bad public communication begins. People hear climate change and imagine a smooth upward slope in temperature, 1 degree. Then another degree, a background hum, a mild drift. That sounds elegant, and it is, but it is also a confession. Because the climate signal is not experienced by human beings as a smooth upward slope. It is experienced as a shift in the probability distribution of extremes. It is experienced as a loaded dice problem. It is experienced as more days near the edge, more storms with deeper moisture, more heat domes with drier soils underneath them, more warm oceans feeding late-season cyclones, more winter atmospheric blockings that sit on top of warmer seas and thinner snowpacks, and therefore behave differently than their historical cousins. This is the key thing. Climate change does not require every day to be unprecedented. It only requires the baseline to shift enough that the tails, the very hot, very wet, very persistent, very strange tails, get populated more often. And once those tails start to populate, events that should have been effectively absent from the observational record start appearing within a single human lifetime. That is not bad luck. That is statistics under a shifted mean, not theory. That is thermodynamics. If you want to understand why the upper atmosphere can suddenly behave in ways that seem detached from everyday weather, you have to stop thinking of the ocean as scenery. The ocean is not scenery. The ocean is the bankroll. Every major atmospheric surprise of the last decade has had an oceanic backstory. The marine heat wave in the North Atlantic that helped turbocharge rainfall extremes over Europe. The extraordinary Gulf of Mexico heat content that fed rapid intensification in tropical cyclones. The record warm waters around parts of Antarctica that collided with already fragile sea ice conditions. The repeated Western Pacific warm pools that have made explosive typhoon intensification look less like an outlier and more like a recurring operational problem. The warm equatorial Pacific during strong El Niño years that reorganizes global convection. The warm Western Indian Ocean that amplifies East African rainfall in some modes and interacts with suppressed rainfall regimes in others. The atmosphere rolls the weather. The ocean loads the dice. And right now, the dice are loaded at multiple latitudes at once. Global sea surface temperature anomalies over the last 2 years have repeatedly sat outside the previous satellite-era range for large portions of the calendar. Not every basin, not every week, but enough of the global ocean has been anomalously warm often enough that the concept of background marine warmth has to be updated. The North Atlantic, in particular, has spent long stretches with anomalies that prompted real concern among oceanographers, not just because the values were high, but because the seasonal timing was wrong. Warmth was appearing too early, persisting too long, and resisting the kinds of cooling episodes that would once have reset the system. Here is why that matters for this story, even though this story began in the stratosphere. A warmer ocean means a moister lower atmosphere. A moister lower atmosphere means more latent heat release when air rises and condenses. More latent heat release means stronger convective towers when the conditions allow them. Stronger tropical convection alters the generation and propagation of planetary waves. Those planetary waves are one of the mechanisms by which the troposphere communicates with the stratosphere. In plain language, unusually warm oceans can help energize the lower atmospheric disturbances that punch upward and disrupt the upper atmosphere. That is not the whole story. It is never the whole story, but it is a big piece. There is a 2001 paper by Baldwin and Dunkerton in Science that is still foundational for how forecasters think about stratosphere-troposphere coupling. A later generation of research built on that and looked in both directions, not just how the stratosphere descends into the troposphere. but how the troposphere preconditions and perturbs the stratosphere. That is where the warm oceans re-enter the frame. They are not merely passive heat sources. They shape the wave field. They shape the convection. They help determine how much of the lower atmosphere's disorder gets communicated upward. Think of the atmosphere like a tall, flexible building. The ocean is the ground it is anchored to. If the ground swells, heats, and becomes uneven, the oscillations of the building change all the way to the top floors. The top floor may be where the dramatic sway is visible. The forcing started below, and this is where the public conversation so often breaks. People want a single villain, a single variable. Was it the polar vortex? Was it El Niño? Was it the warm Atlantic? Was it low Arctic sea ice? Was it a wave-breaking event over Eurasia? Was it the QBO? Was it volcanic aerosol? Was it solar forcing? Yes. No, some of them. Not enough of them. In the wrong order. In the right combination. This is what makes atmospheric science so hard to communicate honestly. The real explanation is rarely one thing. The real explanation is a stack of preconditions, triggers, amplifiers, and feedbacks that line up long enough to produce an event, whose visible surface consequences then get blamed on whichever piece of the stack is easiest to say on television. But the preconditions are everything, and right now the preconditions are extraordinarily permissive. The ocean is warm enough to supercharge moisture transport. The land surfaces in key regions are dry enough to intensify heat when blocking ridges form. The Arctic is altered enough that sea ice and snow cover feedbacks do not behave the way they did 40 years ago. Tropical convection is energetic enough to influence the wave pattern. And the stratosphere is now in a state of disruption large enough to feed back down and reshape the jet. One wave, many faces. That is the phrase you need to keep in your head as we move through the rest of this. Because if you only look for one weather disaster, you will miss the larger thing that is happening. The larger thing is a hemispheric reorganization of probabilities. Different places will experience different symptoms. Some will see cold. Some will see heat. Some will see heavy snow. Some will see prolonged drought under a blocking ridge. Some will see storm tracks displaced into regions that were not expecting them. The event is singular. The consequences are plural, full stop. The jet stream is one of those phrases everybody has heard, and almost nobody has been given a physical picture of. So let me give you one. Imagine a river of fast-moving air, 5 to 9 miles above the ground, driven by temperature contrast. Cold, dense air to the north, warm, less dense air to the south. The sharper the contrast, the stronger the pressure gradient aloft, and the faster the river runs. In a textbook world, that river loops around the hemisphere in a relatively smooth path, guiding storms from west to east. Systems move through. Weather changes. One day you get rain, the next day sunshine, then a front, then a ridge, then another front. The atmosphere breathes. Now distort that river, make it wavier, slow it down. Pull one loop farther north and another loop farther south. Suddenly, a ridge parks itself over one region for days or weeks. Beneath that ridge, skies stay clear, air sinks, soils dry, temperatures climb. And if it is winter, the calm can trap pollution. If it is summer, the heat accumulates with nowhere to go. Under the neighboring trough, cold air keeps pouring south. Storms ride the thermal boundary. Snow machines stay active. Flooding rains repeat. And the same communities get hit again and again because the steering flow will not move on. That is what a meridional, amplified jet does. And a disrupted stratosphere is one of the most effective ways to encourage that amplified state. The physics here are technical, but the consequence is intuitive. When the polar vortex weakens aloft, the belt of westerly momentum that helps keep the upper atmosphere neatly organized slackens. The slack propagates down. The jet stream loses discipline. Rossby waves, the giant planetary undulations in the flow can grow larger in amplitude. Larger amplitude waves move more slowly. Slower waves lock in patterns. Locked-in patterns turn ordinary hazards into compound hazards. Compound hazards are where modern disaster risk lives. A heat wave by itself is dangerous. A heat wave following drought is more dangerous because the dry soils stop evaporative cooling. A cold snap by itself is dangerous. A cold snap following heavy rain is more dangerous because saturated ground and ice loading bring down trees and power lines. A coastal storm by itself is dangerous. A coastal storm landing on top of elevated seas, king tide timing and communities still rebuilding from prior damage is a different category of problem. An atmospheric river by itself is dangerous. An atmospheric river into burned scars or saturated slopes becomes debris flow territory. The jet stream is the traffic controller for all of that. When it behaves normally, risk gets distributed. When it stalls, risk compounds. This is why the current upper atmospheric event is not just a curiosity for people who read weather forums. It is a threat multiplier. In North America, a deep trough over the central or eastern part of the continent can coexist with a massive ridge over the northeast Pacific or western North America. That means one region freezes, while another bakes under anomalous warmth and dryness. In Europe, a Scandinavian block can divert Atlantic storms northward, while drawing bitter continental air westward across the United Kingdom and Western Europe. In East Asia, a displaced jet can lock Japan into repeated heavy snow setups, while northern China alternates between severe cold and dusty dry intrusions, depending on the exact placement of the trough axis. In the Middle East and Mediterranean, blocking can either prolong abnormal warmth and dryness or suddenly collapse into high-impact cyclonic episodes when the ridge breaks. This is the thing most people miss when they ask whether the atmosphere is making weather colder or warmer. That is not the right question. The right question is whether the atmosphere is making patterns stickier, because sticky patterns are what convert anomalies into disasters. There is a reason a 2021 review in Science by Michael Mann and colleagues focused heavily on the concept of amplified Rossby waves and the connection between stalled patterns and extremes. Some of the details remain debated. That is normal in active science, but the operational reality is not debated by the emergency managers dealing with the aftermath. When the atmosphere stalls, impacts pile up. And that is where this event becomes far more than a winter story. Because once the jet learns a slower, wavier posture, even temporarily, the hazard expression changes by season and region. Winter blocking can mean cold outbreaks and snow bombs. Spring blocking can mean repeated severe weather corridors on the warm flank and flood events, where the storm track rides the same boundary over and over. Summer blocking can mean heat domes, crop stress, wildfires, and catastrophic nighttime temperatures that never cool enough for the human body to recover. Autumn blocking can mean drought persistence in one basin, while another gets rain delivered in damaging bursts. One upper air reorganization, multiple surface emergencies, different headlines. Same machinery. That is why it is such a mistake to reduce this story to polar vortex collapse or crazy winter incoming or any other slogan small enough to fit on a thumbnail. The thumbnail version is wrong because it is too small. The atmosphere is not selecting one mode of danger, it is widening the menu. And if the current state persists as long as some ensemble members suggest, the menu is going to change faster than local infrastructure, local media, and local emergency management cultures are used to adapting. The window is closing in some places before the warning language has caught up. Sit with that for a moment. The public still tends to think in single weather mode. One storm, one map, one anomaly, one season. That is how weather was packaged for television for decades, and it made sense because television had limited minutes and the atmosphere, for long stretches of the 20th century, stayed close enough to its historical rails that single-event framing was often good enough. It is not good enough now. A reorganized jet stream can produce simultaneous extremes that look contradictory if you do not understand the geometry. Picture a giant wave in the upper atmosphere. Where the wave bulges northward, warm air surges poleward beneath a ridge. Compression and subsidence warm the air further. Skies often clear. Soil dries. Heat accumulates. Fire weather can escalate if fuels are available and winds increase on the flanks. On the downstream side of the ridge, the flow turns southward into a trough. Cold air drains equatorward. Storm systems follow the baroclinic boundary where hot and cold air masses collide. Moisture streams poleward into the frontal zone. Rain or snow repeats along the same corridor. Meanwhile, somewhere under the knot between those two features, a blocking high or cutoff low can park itself and make the whole arrangement linger. So yes, one atmospheric regime can generate heat, cold, drought, heavy snow, flash flooding, coastal storms, and severe convective outbreaks in overlapping windows. This is not a contradiction. It is the design, and here is where the current event becomes even more consequential. The downstream probabilities are not being laid onto a neutral baseline. They are being laid onto a world in which warmer oceans feed more moisture into storms. Warmer nights reduce recovery from heat. Warmer Gulf waters alter winter cyclone intensification. Warmer atmospheric moisture content increases rainfall efficiency, and many land surfaces are already primed, either too dry, too wet, or too warm, before the new pattern even arrives. That means a cold outbreak can still happen in a warming world, and when it does happen, it may coexist with extreme warmth somewhere else. People who treat those facts as mutually exclusive are telling you, without meaning to, that they do not understand how a wavy jet works. This is the direct address moment. You are going to hear over the next several weeks some version of the phrase, "So much for global warming." If a major cold outbreak occurs, if snow buries a city, if temperatures crash below records in a region unprepared for it, and the phrase will sound intuitively satisfying to people who experience weather locally rather than systemically. It will also be wrong, because the climate signal is not abolished by regional cold. The climate signal is often expressed through the altered persistence, placement, and intensity of the very patterns that deliver regional cold. You can warm the planet and still create violent cold air export events if the circulation becomes more distorted. In fact, in some configurations, that is exactly what the circulation will do. The negative frame matters here. This is not the atmosphere disproving warming. It is the atmosphere redistributing a changing energy budget through a distorted circulation pattern. And here is the part that should stop you cold. The same event that increases cold risk for one latitude band may increase fire weather risk for another. A blocking ridge that channels Arctic air south on its eastern flank can simultaneously bake and dry the western side of the continent. If you are only watching the cold side, you miss the heat side. If you are only watching the snow side, you miss the drought side. This is why the old one disaster at a time mindset fails under modern conditions. Emergency management systems are still organized around hazard silos, heat offices, flood offices, winter weather offices, fire weather offices, utility restoration teams, agricultural drought teams, public health heat response teams. The atmosphere does not care. The atmosphere will happily produce a pattern that stresses all of them in sequence or at once. And once you understand that, the phrase, "the atmosphere just did something nobody alive has ever seen," stops being about drama and starts being about logistics. How do you allocate grid reserves when one region needs heating load and another region is under dangerous warmth? How do you position road treatment assets if the ensemble keeps shifting the trough axis by 400 miles because the upper air initialization is outside the analog space? How do you communicate flood risk honestly when the same audience is also staring at headlines about snow somewhere else and assuming the system must be balanced and therefore safe? These are not abstract questions. These are operational questions. And they all begin with the same truth. One hemispheric atmospheric reorganization can express itself as several seemingly unrelated regional crises. The crises are not unrelated. They are siblings. The atmosphere is one system. We keep mistaking the symptoms for separate diseases. Let me walk you through one of the biggest errors in public weather discourse. Because if this event unfolds the way a significant subset of ensemble guidance suggests it could, you are going to hear this error repeated over and over until it hardens into common sense. The error is this: if cold air still exists, warming must not be that serious. That sounds reasonable until you remember what weather actually is. Weather is motion. Weather is transport. Weather is the atmosphere trying endlessly to reduce imbalances by moving heat, moisture, and momentum around. A warmer climate does not remove motion. It changes the gradients, reservoirs, and pathways through which motion happens. Arctic air still exists. It can still become intensely cold relative to the mid-latitudes. Snow and ice still form. Polar night still cools high latitudes. A weakened polar vortex does not create cold air out of nothing. It changes where the cold air goes. It changes how efficiently it is bottled up versus spilled out. In some winters, the cold remains trapped at high latitudes and large mid-latitude populations see anomalous warmth. In others, the atmospheric pattern allows the cold to escape southward in concentrated pulses. That is not evidence against a warming world. That is evidence of a dynamic atmosphere superimposed on a warming world. And in some ways, the warming can make the impacts of cold outbreaks worse, even when the cold air itself is not colder than historical analogs. How? Infrastructure. Many places are less prepared for cold because long-term averages are shifting warmer. Buildings, pipes, crops, road treatment budgets, grid winterization standards, and public behavior adapt to the climatology they think they live in. If that climatology warms overall but remains capable of sudden severe cold intrusions, the rare cold can strike a system that has become less resilient to it. You saw this in Texas in 2021. The physical cold was severe, yes, but the catastrophe was not just meteorological, it was infrastructural. Generation assets froze, gas supply chains seized, instrument lines iced. Insulation was inadequate. Governance assumptions failed. The disaster was a collision between atmospheric anomaly and system design. That is the template you should keep in mind now. Not because the exact same thing will happen everywhere. It will not. But because every future cold outbreak has to be evaluated not just against temperature records, but against preparedness baselines. A city that can survive -10 Celsius in 1980 may not survive it as well in 2026 if the population has grown. The grid is more tightly optimized. The supply chains are more brittle. And the winters immediately preceding it were so mild that social memory of risk has faded. The numbers do not just get worse, they break, and cold is only half the misunderstanding. The other half is snowfall. A warmer atmosphere can produce more intense snowfall events in places that remain cold enough for snow, because the warmer atmosphere can carry more moisture. This is one of those facts that sounds contradictory until you separate thermodynamics from phase. If the air column is below freezing where precipitation forms and where it falls, more moisture can mean heavier snow rates. If temperatures hover near freezing, warming shifts snow to rain. Both statements can be true in different regimes. This is why some regions may see fewer snow days overall, but more extreme snowstorms when the setup aligns. That is the problem with single-sentence climate takes. They flatten a multi-dimensional system into a slogan and then act surprised when the slogan fails. The better sentence is this: warming changes the character of winter, and part of that changed character can include more volatile swings, heavier precipitation, higher impact ice events, and damaging cold intrusions delivered by distorted circulation, even as the seasonal mean trends warmer. It is more words. It is also true. And truth here matters because the atmosphere is already difficult enough to forecast without the public conversation sabotaging itself. If people interpret every cold event as proof that the larger climate framework is wrong, then every warning that depends on understanding the larger framework becomes harder to communicate. Officials become more cautious with language, audiences become more cynical, attention fractures, the information environment degrades. This is why the misinformation problem is not a side issue. It is part of the hazard. If you misunderstand what cold means in a warming climate, you misread the warning map. If you misread the warning map, you prepare badly. If you prepare badly, the same meteorological event produces a larger human disaster than it needed to. That is not a rhetorical point. That is the pathway from a bad concept to a dead grid. Now flip the map. Take the same amplified wave pattern that exports Arctic air southward in one sector of the hemisphere and look at the region under the ridge upstream or downstream of that trough. That ridge is not a neutral place. It is a compression machine. Air sinks beneath high pressure. As it sinks, it compresses. As it compresses, it warms. Clouds are suppressed. Incoming solar radiation reaches the surface more efficiently. Soil moisture evaporates. If the land is already dry, the missing moisture means less energy is spent evaporating water, and more energy goes straight into heating the air. Nights stay warmer if the air mass is thick and stagnant. Vegetation stress accumulates. Electric demand rises. Air quality worsens. And if there is wind on the ridge flank, wildfire risk can escalate quickly. This is how one upper air configuration can produce extreme cold headlines in one region and dangerous warmth in another. It can also do this in the same country. There have been winters in North America where Alaska or Western Canada baked under exceptional warmth while the central or eastern United States froze. There have been European setups where Scandinavia or Greenland ran extraordinarily warm while Western Europe dealt with cold continental flow. These are not oddities. They are geometric consequences of amplified flow, but here is the part that is changing. When the ridge side of the pattern develops over an already warmed baseline, the heat does not need to be historic by circulation alone to become historic in impact. A ridge that would once have produced an unusually warm spell can now produce record night temperatures, earlier snowmelt, premature vegetation emergence, intensified evaporation, and a larger fire weather footprint because the background from which it started is hotter than it used to be. That is the ratchet effect. The ratchet clicks down, the baseline rises. The same synoptic pattern now lands higher on the scale. This is why the phrase new normal is so inadequate. There is not one new normal. There are many region-specific baselines being pushed around by a circulation that itself is becoming more volatile in some dimensions. One place gets heat that used to require a blockbuster ridge. Another place gets flood that used to require a tropical feed of moisture. Another place gets winter rain instead of snow, and therefore a very different hydrologic outcome from the same moisture plume. The atmosphere is not giving us one new world. It is giving us many local worlds stitched together by the same planetary physics. And again, The current upper atmospheric anomaly matters because of timing. If this stratospheric disruption feeds into a slower, more amplified jet through a seasonal transition, the hazards can mutate as the weeks pass. What begins as a cold risk in one region can evolve into flood risk as the storm track locks into a boundary and repeatedly overruns cold air. What begins as a warm, dry pattern can evolve into early fire weather. What begins as a snow event can become a catastrophic ice event if warm air intrudes aloft. The pattern can persist while the expression changes. That is what makes persistence so dangerous. It is not just that one hazard lasts longer. It is that the same circulation regime can deliver a sequence of hazards without giving systems time to recover. Emergency managers understand this viscerally. Recovery windows matter. If crews are still replacing transformers from a cold outbreak when a windstorm hits, capacity is lower. If soils are still saturated from one storm when the next atmospheric river arrives, flood response degrades. If a community has spent weeks under smoke or heat, public health resilience is already weakened before the next event arrives. The window is closing. And the atmosphere does not wait for the spreadsheet to catch up. Whenever the atmosphere does something visually dramatic or statistically rare, a familiar ecosystem comes alive online. Screenshots of radar artifacts, claims about ionospheric heaters, assertions that clouds do not move naturally that way, cherry-picked satellite loops, phrases like "they're controlling the weather." And because the real atmosphere is complicated, and because public science education has not kept pace with the complexity of the system, those claims can spread faster than the actual explanation. So let's do this properly. The false claim is that humans are directly engineering atmospheric patterns of this scale in real time, steering storms, manufacturing stratospheric anomalies, or forcing planetary wave behavior on demand through secret technologies. That claim is wrong. It is wrong for reasons of energy, scale, control, and observable mechanism. Start with energy. The atmosphere is enormous. The latent heat released by a major mid-latitude cyclone or by a strongly organized convective complex is on a scale that dwarfs the output of any plausible human-operated directed energy system by absurd margins. The total daily solar energy entering the Earth system is roughly 173,000 terawatts. Human civilization uses on the order of tens of terawatts. Let that ratio breathe for a second. Weather is operating inside a power system vastly larger than anything we can manipulate with engineering infrastructure built on the surface. Now scale. The current anomaly we are talking about is hemispheric. It spans vertical layers from the troposphere into the stratosphere. It interacts with planetary waves thousands of kilometers long. To engineer a pattern like that on demand would require not just enormous energy, but a mechanism for applying that energy with extraordinary spatial precision across a rotating fluid shell, under constant solar forcing and chaotic nonlinear feedback. There is no evidence for such a mechanism. There is also no evidence in the observational record, satellites, radiosondes, reanalysis, chemistry profiles, ionospheric measurements of a hidden forcing signature remotely capable of producing what is being observed. Third, control. Even small-scale weather modification efforts like cloud seeding have limited, conditional, highly localized effects, and even those remain difficult to quantify cleanly in operational settings. They are not steering jet streams. They are not creating or splitting polar vortices. They are not rearranging stratospheric temperature structure over half a hemisphere. Confusing localized precipitation enhancement research with hemispheric circulation control is like confusing a garden hose with a plate tectonics machine. And finally, mechanism. The actual mechanisms behind this event are known. Not known in every detail, not perfectly forecast, but known in the sense that they are physically grounded, observable, and reproducible in research frameworks. Planetary wave propagation, wave breaking, momentum deposition, stratospheric warming, vortex disruption, downward coupling, jet amplification, teleconnection shifts. We can watch pieces of this happen in the data. We can simulate pieces of it in models. We can compare it to prior events. We can argue about the margins and still agree on the machinery. So no, this is not somebody pushing a button, but here is the rhetorical pivot. The real explanation is actually more alarming than the conspiracy. Because the real explanation is not that a small group of people secretly controls the weather. The real explanation is that billions of people openly altered the composition of the atmosphere, heated the ocean, changed the land's surface, and increased the energy available to the system. And now the system is producing outputs that no single actor controls, and no single government can fully stop in the short term. That is harder to fit on a meme. It is also much scarier. Conspiracy frameworks are emotionally attractive because they imply authorship, and authorship implies intent, and intent implies the possibility of confrontation. If someone is doing this, then perhaps stopping them would stop the problem. But climate-scale atmospheric disruption is not a villain of the week story. It is an accumulated physics story. It is chemistry, ocean heat content, land-atmosphere feedback, risk exposure, infrastructure design, and statistical baselines all grinding against one another until the old assumptions fail. That is why the false explanation spreads so easily. It is simpler. It flatters intuition. It transforms a diffuse systems problem into a solvable morality play. Reality is less cinematic. Reality is that the atmosphere is responding to boundary conditions we changed over generations. Reality is that the response emerges through nonlinear fluid dynamics most people have never been taught to visualize. Reality is that by the time the pattern is visible enough for a viral post, the preconditions that made it possible were already years in the making. The explanation is complete. And there is another cost to conspiracy framing that matters right now. It distracts from the actual actions that reduce risk. If you believe weather is being steered by a hidden machine, you stop paying attention to insulation, wet bulb temperature, grid redundancy, floodplain management, crop choice, cooling centers, building codes, forecast communication, and emission trajectories. You trade the hard reality of adaptation and mitigation for the emotional release of accusation. The atmosphere does not care which story you prefer. It will still do the math. Full stop. This is the point where a lot of atmospheric explanations stop. They give you the charts. They give you the mechanism. They maybe give you the probabilities. And then they end before the part that actually determines whether an anomaly becomes a tragedy. Infrastructure. The modern world was built on assumptions about return periods, about a 1 in 100-year flood, about a design wind speed, about a historical frost line, about what constituted an extreme snow load, an acceptable summer peak demand, a reasonable pipe burst threshold, a plausible wildfire season length, a stable insurance model, a predictable planting window, and a forecastable shoreline retreat rate. Those assumptions are now under stress almost everywhere. And when the atmosphere does something nobody alive has ever seen, it is not just because the air itself is unusual. It is because the atmosphere is colliding with physical systems calibrated to a different distribution. A power grid is designed around expected peak loads and expected failure cascades. A road network is designed around expected freeze-thaw cycles and expected runoff intensities. A reservoir system is designed around expected snowpack timing and expected inflow seasonality. Coastal defenses are designed around expected storm surge probabilities and expected sea level baselines. Crop calendars are designed around expected last freeze and first freeze windows. Insurance portfolios are priced around expected loss frequency. Those are all climate assumptions with engineering attached. Once the baseline moves, the engineering starts to lie. A 2023 report from the First Street Foundation made headlines because it translated climate risk into property-level exposure in ways that suddenly made insurance and mortgage markets pay attention. But the technical reality behind those headlines is older and deeper. The actuarial models are under strain because the physical distributions are under strain. The return periods are no longer returning on schedule. Events once treated as tail risks are clustering, not always because of random luck, often because the baseline was wrong. This is the recovery gap problem. Imagine a bathtub filling from the faucet while the drain is partially clogged. In the old climate, major damaging events were spaced out enough that communities could drain between them. Rebuild, refinance, repair, restore emergency funds, replace transformers, replant fields. Reopen schools, recover psychologically. In the new climate, the faucet is running faster and the drain is slower because each event is more expensive, more complicated, and more likely to be followed quickly by another. The water level rises not because any one event is singularly apocalyptic, but because the system no longer gets enough time to empty. That is the slow-motion catastrophe. And this current atmospheric event slots directly into that framework because of persistence. A sticky jet stream does not merely threaten one place once. It threatens multiple places in sequence while each place is already operating under thinner margins. A week of abnormal cold can stress transformers and gas systems. The thaw can flood. The next wave can refreeze. Supply chains can jam. Insurance claims stack. Public attention decays. The hazards mutate while the workforce stays the same size. Here is the part that should stop you cold. For many communities, the atmospheric anomaly is no longer the hardest part. The hardest part is surviving the second-order failure cascade after the weather has already happened. Hospitals running on backup power, water treatment plants losing pressure, elderly residents trapped by impassable roads or heat without air conditioning, food spoilage, medication interruptions, school closures, wage losses, mold in flood-damaged homes, rental displacement. Fire stations understaffed because their own families are also in the disaster zone. These are not side effects. They are the disaster. This is why I keep saying the story is not the storm. The story is the system. And when the system was built for the old climate, every unprecedented atmospheric configuration becomes a test not just of meteorology but of social design. Who has backup? Who does not? Who can evacuate? Who cannot? Who can absorb another insurance deductible? Who is already uninsured? Who gets warned in time? Who gets warning fatigue because this is the fourth major alert in 6 months? The floor has risen. The room for error has shrunk. That is where we actually live now. Let me stay here, because if you want to understand why so many communities feel like they are in a permanent state of near disaster, even in years without one singular historic headline event. This is the mechanism. Recovery used to be seasonal. You had storm season, fire season, winter, monsoon, maybe a spring flood, maybe a summer heat wave. Bad years happened, yes, but there was enough temporal separation that institutions could still pretend each event was discrete. Local government could close the books, apply for assistance, make repairs, and tell itself that the next test would likely come later. That calendar is becoming unreliable. Now a community can be hit by smoke, then flood, then heat, then drought, then a grid emergency, then another flood. Not because the earth has abandoned all pattern, but because the patterns themselves are getting more persistent, more moisture-laden, more seasonally displaced, or more tightly sequenced than the systems for response were built to handle. The recovery gap is the distance between how fast a place can repair itself and how fast the next damaging event arrives. If the repair time is longer than the event interval, the gap widens. If the gap widens, damage accumulates in layers. If damage accumulates in layers, vulnerability stops being an emergency condition and becomes the baseline. That is the hidden climate statistic. Not just how hot it got, or how much rain fell, or how deep the snow was, but whether the next event arrived before the previous one was metabolized socially, financially, and physically. And when a major upper atmospheric reorganization creates weeks of pattern persistence, it compresses those windows even further. One city gets the flood, another gets the cold, another gets the warmth. National media moves on, utility crews do not, supply chains do not, insurance markets do not, municipal budgets do not. There is a 2018 paper in Nature Climate Change by Agha Kuchak and colleagues that looked at compound extremes and stressed what emergency managers already understood intuitively. Hazards interact. Heat and drought, rain and wind, surge and rainfall, fire and debris flow. Once you think in compound hazards instead of isolated ones, the recovery gap becomes obvious. The relevant unit is not the storm. The relevant unit is the sequence. And this is where human attention becomes part of the problem. We are good at responding to singular drama. We are bad at recognizing attritional systems failure. A single Category 5 landfall gets wall-to-wall coverage. A county that spends 9 months under a stack of moderate to severe disruptions gets far less. But from a resilience perspective, the county under repeated, moderate events can end up in a deeper hole. This is the mismatch between spectacle and stress. The atmosphere does not care whether an event is cinematic. It only cares about physics. A pattern that keeps producing moderately destructive outcomes can hollow out a region just as effectively as one iconic catastrophe, especially if the insurance, labor, and public health consequences cascade over time. So as this event unfolds, watch not just the weather maps, watch the spacing, watch the lead times, watch whether the same infrastructure appears in the story twice. Watch whether counties still under one emergency declaration get hit with another watch or warning. Watch whether schools pivot from closure to cooling center to shelter in a single month. That is where the future is showing itself, not in one monster event, in the compression between them. There is a meta layer in every modern weather disaster, and if you ignore it, you misunderstand the event. The atmosphere produces physical signals. Forecast centers turn those signals into products. Media translates those products into stories. Social media strips the stories into fragments. Conspiracy ecosystems remix the fragments into narratives. Audiences receive all of it through stress, ideology, memory, and personal experience. Then they decide whether to act. That is not adjacent to the hazard. It is part of the hazard. Because a warning that arrives in a polluted information environment does not land the same way as a warning that arrives in a trusted one. If audiences have been trained by years of overhyped thumbnails and underexplained science to believe every unusual weather chart is either a hoax or the apocalypse, then a genuinely extraordinary event lands in a population already numbed, polarized, and suspicious. This is alert saturation. And alert saturation is deadly because it makes rare high-signal warnings compete with a constant background roar of lesser notifications, recycled climate takes, weather influencer exaggeration, and screenshot-based pseudo-analysis. The National Weather Service has been wrestling with this for years. So have emergency managers in Europe, Japan, Australia, and elsewhere. How do you issue urgent language often enough to be useful, without training the public to ignore urgency as just another flavor of weather content. How do you explain uncertainty, honestly, without sounding weak? How do you escalate language when the science itself is telling you this is outside the known range, but your audience has heard historic 10 times already this season? This is the communication trap of the new climate. The old language was built for a world where exceptional events were exceptional enough that words like unprecedented retained most of their voltage. Now the events are coming often enough, or the headlines are using the language loosely enough, that the vocabulary itself is degrading. That matters right now because the event we are talking about really does deserve unusual language. But unusual language in a saturated environment can paradoxically be less effective, not more. It sounds like one more exaggerated claim, unless the audience has enough trust in the source to know the difference. That is why credibility signals matter so much. Named papers, named agencies. Distinguishing what is observed from what is modeled. Stating uncertainty without understating stakes. Saying we do not know exactly where the trough axis will settle yet, and then immediately explaining what we do know. The goal is not to sound dramatic. The goal is to sound precise enough that the public can tell the difference between a real signal and a content machine. And here is the part that should stop you cold. As the atmosphere becomes harder to summarize cleanly, bad information gains a structural advantage. The false explanation is often simpler, cleaner, and more emotionally satisfying than the true one. They did this beats. A coupled nonlinear fluid system under altered boundary conditions produced a hybrid stratospheric disruption with unusually uncertain downward propagation. Of course it does. One sentence gives you a villain, the other gives you homework. So the people trying to communicate the real risk are always starting a few steps behind. They are asking the public for patience, nuance, and systems thinking in the middle of a culture that rewards speed, certainty, and outrage. This is not a side note. This is why honest weather communication now feels almost like a form of emergency medicine. The science has to be right, yes. But the translation also has to cut through a psychological and informational climate that is itself already in crisis. That is why I am taking this slowly. Not because the event is simple. Because it is not. And if you simplify it too far, you begin lying without meaning to. A lot of people hear, the models don't agree, and translate that to, the models don't know anything. That is not how this works. Models can correctly identify a dangerous regime and still disagree sharply on its exact expression. Think of it this way. If you know a river is about to flood, you can still be uncertain about which streets will go under first, how fast the water will rise at a particular bridge, or which levee segment is most likely to fail. The broad hazard can be clear while the operational details remain uncertain. That is where we are with this event. The ensemble systems, the American GFS ensemble, the ECMWF ensemble, the Canadian, the Japanese, the subseasonal products, are all seeing the same broad thing, a disrupted stratosphere, a high probability of downward coupling, and an increased risk of amplified mid-latitude flow. That is the signal. Where they diverge is in the details that actually determine who gets what weather and when. How quickly does the signal descend? Does the dominant trough set up over eastern North America or farther west? Does blocking lock over Greenland, Scandinavia, the North Pacific, or some rotating combination? Does the stratospheric anomaly remain coherent long enough to reinforce the lower pattern? Or does it fragment in a way that produces shorter, more chaotic pulses? Do the tropical forcings line up constructively or destructively with the mid-latitude pattern? Does the MJO assist or interfere? Does the QBO phase subtly alter the probability of persistence? Does snow cover in Siberia or North America alter the feedbacks at the surface? These sound like details. They are not. They are the whole downstream forecast. And because the current upper air state is so unusual, small differences in how a model handles wave breaking, momentum deposition, or vertical coupling can produce large differences in the surface solution 10 or 20 days later. This is the butterfly effect people invoke carelessly, except this time it is actually grounded in the physics of initialization outside the analog space. A model is only as comfortable as the climates it has practiced on. That does not mean the models are useless in a changed climate. Far from it. It means you have to read them differently. You focus less on deterministic snapshots and more on scenario clusters. You ask what outcomes appear across many ensemble members. You look for stable probabilities rather than seductive precision. You stop treating the 10-day chart shared on social media like a prophecy and start treating it like one branch in a distribution. Operational meteorologists know this. Many audiences do not. And this is where communication matters again. Because when the public sees forecasts changing from day to day, it often interprets that as incompetence. In reality, changing forecasts during a high uncertainty regime can be evidence of honesty. The models are ingesting new observations from the stratosphere, the ocean, the surface, aircraft, satellites, radiosondes. They are updating. The forecast shifts because the system is shifting and the understanding improves. That is what good science looks like under uncertainty, not certainty theater, revision. A 2019 review in Bulletin of the American Meteorological Society on forecast communication emphasized this tension repeatedly. Users want definitive answers. The atmosphere often supplies only probabilities. The solution is not to fake certainty. The solution is to teach the public how to think probabilistically without losing the urgency signal. Easier said than done, but crucial now. Because if this event evolves into the kind of prolonged hemispheric pattern shift that some model clusters indicate, you are going to see maps swing, headlines contradict, and hot takes age badly within 48 hours. The wrong conclusion will be, nobody knows anything. The right conclusion will be, the large-scale threat is real, and the exact local expression remains fluid because the system is outside its comfort zone. That is a harder sentence. It is also the only useful one. I want to zoom out now, because this is where the deepest misunderstanding happens. People hear phrases like new normal, and they imagine a new average day. Slightly warmer summer, milder winter, more humid afternoon, a few more bad storms, something like the old climate with the knobs turned modestly upward. That is not the new normal. The new normal is volatility laid on top of trend. The new normal is a higher floor for heat, a wetter ceiling for rainfall, a more loaded probability distribution for extremes, and a public infrastructure system that still, in too many places, assumes the old bell curve is coming back. The new normal is not one weather event. It is a world in which the background conditions make exceptional events easier to produce and harder to recover from. That is why this current atmospheric anomaly matters, even if the exact downstream consequences differ from what some ensemble members currently show. Even if the cold ends up less intense in one region, even if the block breaks earlier in another, even if the event underperforms the most aggressive headlines, the state itself is a message. The message is that the atmosphere can now occupy configurations that human observational memory does not contain. Once that becomes true, you are in a different relationship with risk. You can no longer rely on lived experience alone to judge plausibility. "I've never seen this before" stops being comforting. It becomes diagnostic. It tells you the old mental model is too small. And this is the part that most societies resist hardest, because it is not just a scientific adjustment. It is a cultural one. Insurance has to change. Engineering has to change. Agriculture has to change. Urban planning has to change. Energy systems have to change. Public health systems have to change. Media literacy has to change. Education has to change. Because the atmosphere is no longer constrained by the assumptions under which all those systems were designed. The gap is widening. And you can see it in little ways before you see it in catastrophic ones. Farmers shifting planting dates and still getting caught by late frosts. Ski resorts making snow in windows that used to be naturally reliable. Grid operators issuing conservation requests in seasons that were once low risk. Coastal communities flooding on tides that no longer require dramatic storms. Parents checking air quality indices in regions where wildfire smoke was once a distant problem. Emergency managers learning the phrase compound event, not from an academic paper, but from a week that never stops escalating. This is what the new normal looks like from the inside. Not a cinematic apocalypse, a growing mismatch between what the atmosphere can now do and what society still assumes it will do. That mismatch is the story. And the current event, the one nobody alive has seen before in the modern observational sense, is not important because it is singular. It is important because it shows how far the system has drifted from the rails we thought defined it. The atmosphere is giving us a preview of its wider operating range. We should be paying attention. So what should you actually watch now? Not the hype, not the thumbnail version. The real signals. First, watch for evidence of downward propagation in the zonal wind anomalies. If the stratospheric disruption continues to descend layer by layer toward the troposphere, confidence rises that the surface jet will remain amplified. This is one of the cleanest indicators that the upper air anomaly is not just a transient curiosity. Second, watch the blocking signatures over Greenland, the North Atlantic, Scandinavia, and the North Pacific. These are the anchor points. If the blocks lock in, storm tracks and temperature anomalies downstream become more persistent. If they remain mobile, the impacts may still be severe but more episodic. Third, watch tropical convection. The MJO, equatorial Pacific patterns, and subtropical moisture transport are not side players. If tropical forcing aligns with the extratropical wave pattern, the resulting amplification can be stronger and more coherent. If it interferes destructively, some of the most extreme scenarios can be blunted. Fourth, watch the soil moisture and snow cover maps. People underestimate these because they are less dramatic than satellite loops, but land surface conditions determine how atmospheric anomalies translate into actual sensible impacts. Dry soils intensify heat. Snow cover amplifies cold at the surface. Saturated ground makes moderate rain more dangerous than it would otherwise be. Fifth, watch the official forecast language. Not just the icons, the words. When forecast offices start emphasizing persistence, uncertainty in placement but confidence in regime, repeat hazards, infrastructure stress, and preparedness windows, that is often where the most useful intelligence is. The exact snowfall map 7 days out may shift. The language about the regime often tells you more. And finally, watch the spacing between events. I keep coming back to this because it matters. If the same basin is under repeated warnings, if the same corridor keeps seeing storm track alignment, if the same communities lose the same infrastructure twice in a short interval, that is the moment to stop asking whether the weather is back to normal and start asking whether the regime itself has changed. Because that is the deeper risk here. Not one spectacular outbreak, not one weird map, a weeks-long rearrangement of atmospheric traffic over a civilization built for older lanes. And now we arrive at the question that makes all of this so hard to package honestly. We do not yet know whether this event is a statistical outlier within a still recognizable system. or whether it is one of the first clean signals that the operating envelope of the atmosphere has widened faster than our forecasting culture, our infrastructure, and our public language are prepared to admit. That distinction matters. If this is merely a once-in-many-decades freak alignment of wave forcing, ocean state, seasonal timing, and stratospheric predisposition, then it will still be historically significant, still operationally consequential, and still worth studying for years. But it would live mostly as a warning about the tails. If instead this is an early example of what the atmosphere looks like when a warmer ocean, altered cryosphere, shifted moisture reservoir, and more permissive background state begin to populate the outer edges of possibility more often, then this is not a one-off. It is a threshold crossing, and here is the uncomfortable truth. We may not know which of those two frames is correct for years. Science is slower than weather. Attribution studies take time. Reanalyses take time. Comparative event diagnostics take time. Papers get written after the damage. The atmosphere moves now. Understanding catches up later. That lag is built into the story. It is one reason the information environment becomes so distorted around events like this. People want verdicts immediately. Was this climate change? Was this natural variability? Was this unprecedented in the true statistical sense or only within modern observation? Is this the future or a fluke? Those are fair questions. But the atmosphere does not owe us immediate epistemological closure. Sometimes the honest answer is, the signal is real, the implications are serious, and the classification will take time. That is not a weak answer. It is a scientific answer. And maybe that is the hardest thing for modern audiences to tolerate, not danger, but unresolved danger. Not a dramatic ending, but an open loop. Because an open loop requires attention. It requires memory. It requires staying with the story after the headline decays. That is what this event is demanding from us now. Not panic, not denial, not theatrics, attention. Sustained, technically literate, emotionally steady attention, because the atmosphere has just shown us something that does not fit the old mental archive. And whether this becomes a historical curiosity or the early chapter of a much larger pattern depends not only on what the atmosphere does next, but on whether we are willing to understand what we are looking at while it is still unfolding. This is not the end of the story. That is the story. Right now, somewhere above the weather you can feel and the headlines you can see, the atmosphere is still rearranging itself. The stratospheric anomaly is still there. The wave geometry is still evolving. The models are still ingesting new data and revising the edges of the forecast. The oceans below are still warm. The land surfaces are still carrying the memory of the last extremes. The infrastructure is still calibrated to assumptions from a smaller energy world. The information environment is still noisy enough to confuse people about what matters. The recovery windows are still too short. The baselines are still rising. The dice are still loaded. And the most dangerous mistake at moments like this is to assume that once the first visible symptom passes, the underlying story has passed with it. It has not. Because what the atmosphere just did was not simply produce one unusual event. It revealed range. It showed us that the coupled system we live inside can occupy states beyond lived memory and beyond the clean analog catalogs we relied on for confidence. It reminded us that historical experience is no longer a sufficient map of future plausibility. It exposed, again, the gap between the climate the world was built for and the climate that is now arriving in uneven, violent, technically fascinating, deeply consequential bursts. This is not hyperbole. This is what it means to live inside a fluid system whose boundaries have been moved. So if you take one thing from this entire video, let it be this. The atmosphere is not broken. The old expectations are. And once you understand that, the headlines begin to read differently. The strange winter outbreak is not an isolated oddity. The stalled flood pattern is not bad luck. The simultaneous heat and cold are not contradictions. The forecast uncertainty is not necessarily incompetence. The public confusion is not random. The rising insurance costs are not overreaction. The repeated strain on the same communities is not coincidence. These are all pieces of the same system trying to express a new energy reality through institutions still designed for the old one. That is why it is far from over, not because doom is inevitable, not because every forecast will verify at the worst end of the range, not because every anomaly is the new permanent state, but because the underlying drivers that made this possible are still in place. The ocean has not cooled back to 20th century norms. The radiative imbalance has not vanished. The infrastructure has not fully adapted. The public language has not caught up. The models are improving, yes, but the atmosphere is exploring its own widened space at the same time. We are learning the new system while living inside it, and that means every event like this does double duty. It is a forecast challenge in the present tense, and it is a message from the future tense. The question is not whether the atmosphere will calm down forever after this one. The question is how often a system with this much added energy, this much stored ocean heat, this much altered land surface, this much changed cryosphere, and this much social exposure is going to find new ways to surprise us. That is the open question. That is the one nobody can answer yet. And that is why, if you are paying attention, the most honest ending is not relief. It is vigilance. Because the atmosphere just did something nobody alive has ever seen, and it is far from over. There is a quiet assumption embedded in nearly every modern institution that touches the weather, and it almost never gets stated out loud. The assumption is that the climate of the last 50 to 100 years is the climate of the next 50 to 100 years. Not perfectly, not statically, but close enough that the engineering tolerances, the actuarial tables, the building codes, the planting calendars, and the public risk perceptions built around that period would remain broadly valid. That assumption was never a contract. It was a convenience, a working approximation, a useful fiction, a statistical shorthand that allowed enormous infrastructure decisions to be made without having to constantly relitigate the underlying physical baseline. For most of the 20th century, the convenience worked. The climate drifted slowly enough relative to the speed of human decision-making that you could treat it as effectively stationary inside the planning horizon of a bridge, a sewer system, a transmission line, a crop variety, a flood map, or an insurance policy. The atmosphere was not actually stationary. It never has been, but it moved slowly enough that pretending it was stationary did not produce constant catastrophic surprises. That period is ending. Not ending in the sense that the calendar has a hard cutoff. Ending in the sense that the assumption of approximate stationarity is breaking down for more and more variables simultaneously. Heat extremes, precipitation extremes, sea surface temperatures, snowpack reliability, fire weather indices, drought persistence, tropical cyclone intensification rates, compound event likelihood, stratospheric behavior, jet stream geometry. All of them are showing changes large enough that the stationarity shortcut is no longer safe to lean on. A 2008 paper in Science by Milley and colleagues had a title that aged into prophecy. Stationarity, they argued, is dead. They were writing about water resource planning. The argument has since generalized to nearly every domain that depends on climate distributions. You cannot design for the past mean when the mean itself is moving. You cannot price the past tail when the tail is fattening. You cannot teach the public to expect the historical norm when the norm has been quietly walking off the chart. Let me say that again so it registers. The historical baseline was a useful approximation, and the approximation is failing. That does not mean we throw away history. History is still the only training dataset we have, but history must be used differently now, as a floor, not a ceiling. As an indication of what was possible under prior conditions, not a guarantee of what is possible under current ones. As a foundation for understanding mechanisms, not as a forecast for outcomes. This is why events like the current stratospheric anomaly feel so destabilizing to people whose intuition was trained on stationarity. The intuition expects the system to misbehave inside known bounds. The system instead is misbehaving in directions that previous decades did not document. That is not the system breaking the rules. That is the system using more of its rulebook than humans have personally witnessed. And here is the part that should stop you cold. The rulebook itself is not infinite. There are physical constraints on what a coupled ocean-atmosphere-land system can do, even under significant forcing. Energy conservation still applies. Angular momentum still applies. Thermodynamic limits still apply. So no, the atmosphere is not heading toward arbitrary chaos. It is heading toward different configurations within physical limits. We are only beginning to fully sample observationally. That distinction matters because it pushes back against two equally dangerous narratives. The first narrative says nothing unusual is happening because the planet has always had extreme events. The second says we are heading for an unbounded breakdown of physical order. Both are wrong. The first underestimates the magnitude of the shift in distributions. The second overestimates the destination by ignoring the constraints. The truth is harder to fit into a slogan. The truth is that we are watching a real, bounded, but significant migration of the operating envelope of the atmosphere into regions that human civilization has not previously had to function within at this scale of infrastructure and population. That is the actual story, and it is, in its way, more sobering than either of the simpler narratives, because it cannot be dismissed and cannot be reduced to a single fix. If you want to understand why a stratospheric anomaly today behaves differently than one in 1985, even when the upper air structures look superficially similar, you have to look at the Arctic. The Arctic is not a passive cold reservoir. It is an active component of the global atmospheric circulation, and it has been undergoing some of the most rapid changes anywhere on the planet. Sea ice extent in late summer has declined dramatically since reliable satellite monitoring began in 1979. Multi-year ice, the older, thicker ice that historically provided structural integrity to the Arctic ice pack, has declined even more sharply than total extent. Greenland's ice sheet has been losing mass at accelerating rates, with multiple peer-reviewed studies in journals like the Cryosphere and Nature documenting the trajectory. Permafrost has been thawing across vast stretches of Siberia, Alaska, and northern Canada. Snow cover patterns in spring have shifted earlier in much of the northern hemisphere. These are not isolated changes. They are coupled, and the coupling matters for everything we are talking about in this video. When sea ice retreats, the dark ocean beneath it absorbs more solar radiation in summer. That stored heat must escape somehow before winter, and a great deal of it escapes upward into the atmosphere during autumn, warming the lower polar atmosphere far more than the surface alone would suggest. This warming reduces the temperature contrast between the Arctic and the mid-latitudes, which is one of the main drivers of the strength of the westerly winds aloft. When that contrast weakens, the jet stream loses some of its momentum. When the jet stream loses momentum, it can become more easily distorted by planetary wave forcing. When planetary waves grow larger in amplitude, they can more effectively perturb the stratosphere from below. When the stratosphere is perturbed strongly enough, It can disrupt the polar vortex. When the polar vortex is disrupted, the consequences propagate back down into the troposphere. Do you see the loop? The Arctic is not just receiving climate change. It is participating in shaping how the rest of the hemisphere experiences it. A 2014 paper by Jennifer Francis and Stephen Vavris, building on earlier work, proposed that Arctic amplification, the disproportionately fast warming of the Arctic relative to lower latitudes, could be linked to more frequent extreme weather in mid-latitudes through changes in jet stream behavior. The hypothesis has been refined, contested, supported in some studies, complicated in others. Atmospheric science is rarely tidy. But what is no longer seriously contested is that the Arctic has changed substantially, and that the changes have downstream consequences. The argument is about magnitude and mechanism, not about whether the signal exists. Here is what this means for the current event. The stratospheric anomaly is not happening in isolation. It is happening on top of an Arctic that no longer has the same surface properties, the same sea ice configuration, the same snow cover seasonality, or the same heat flux behavior that earlier reference periods documented. The same stratospheric disruption descending into this Arctic and this hemisphere may not produce the same downstream pattern as a comparable disruption would have produced 40 years ago. The amplifier has changed, and the changed amplifier means that even our understanding of how previous events propagated may not perfectly translate forward. This is part of why the operational forecast confidence is unusual. It is not just that the upper air state is outside the analog space. It is that the lower boundary conditions feeding back into the system have themselves shifted. So the standard mental shortcuts, in past SSWs, X tended to follow Y, have to be applied with care because the environment in which X and Y interacted has been quietly evolving. Sit with that for a moment. The atmosphere is doing something unusual in the upper layers. The lower layers are responding through a system whose boundary conditions have changed. And the data we use to anticipate the consequences was largely collected under conditions that no longer fully apply. This is the real fog of forecasting under climate change, not ignorance, not chaos. A genuine, structural mismatch between the era when our intuition was calibrated and the era we are now trying to forecast through. While the atmosphere has been doing its dramatic, headline-friendly thing in the upper layers, the ocean, quieter, slower, vastly more massive, has been steadily absorbing the bulk of the excess energy the planet has been retaining. This is not a minor detail. It is arguably the most important single fact in modern climate science. More than 90% of the additional energy retained by the Earth system due to greenhouse forcing has gone into the ocean. Not the atmosphere, not the land, not the ice, the ocean. That energy does not disappear. The ocean does not have a venting mechanism that releases it into space on a human timescale. It stays. It mixes downward slowly. It moves around through currents on timescale that range from months at the surface to centuries at depth. And it interacts with the atmosphere through air-sea fluxes, evaporation, convection, and the storm-supporting feedbacks that turn warm surface waters into the fuel for damaging weather. When you hear that 2023 and the years following it shattered records for global ocean heat content, that is not a curiosity. That is the receipt the ocean is keeping. Every record-breaking year of ocean heat is a year in which the system has stored more energy than it can immediately do anything with. That stored energy is available to the atmosphere in ways that take many forms and many timescales. Hurricanes intensifying more rapidly when they cross unusually deep warm pools. Marine heat waves persisting long enough to alter ecosystems, fisheries, and regional weather. Atmospheric moisture content rising in response to warmer sea surfaces, feeding more intense precipitation events when storms tap into those reservoirs. Stratification of the upper ocean intensifying, altering mixing dynamics and nutrient cycling. The ocean is patient. It is also unforgiving. Because once heat is in the upper ocean, removing it is enormously difficult. There is no realistic short-term intervention that draws it back out at the rate it went in. We can stop adding to it. We cannot easily unadd what is already there. This is why even sharp emissions reductions, while absolutely necessary, would not immediately stabilize weather extremes. The ocean would continue to release stored energy into the atmosphere for decades regardless. That is not an argument against mitigation. It is an argument for understanding that mitigation, adaptation, and infrastructure investment must happen simultaneously. You cannot pick one and expect the others to take care of themselves. And this is where the current event reconnects to the larger story. The atmospheric anomaly we are watching unfold in the upper layers is being staged on top of an ocean that has been quietly setting records below. The interaction is not optional. The atmosphere reaches for the ocean every time it organizes a storm, sets up a moisture conveyor, locks in a blocking pattern over warm waters, or pulls subtropical moisture into a mid-latitude trough. Each time, the ocean responds with the energy state it currently holds. A warmer ocean means a more energetic atmospheric response when the geometry aligns. A more amplified jet stream from a disrupted stratosphere means more frequent opportunities for that geometry to align in unusual ways. A more unusual alignment over a warmer ocean produces a more unusual surface outcome. The numbers do not just get worse, they break. This is what is meant by compounding. It is not metaphor. It is the literal stacking of state variables that have all moved in directions that increase the energy available to extremes, while the circulation simultaneously becomes more capable of expressing that energy in concentrated, persistent, region-specific ways. The ocean is keeping the receipts. The atmosphere is presenting the bill. I want to ground this somewhere even more concrete than charts and ensembles, because none of this matters if it stays in the abstract. Walk through any major city. Look at the storm drains. Count them, look at the cross-section of the curb. Look at how far apart the inlets are. Look at the slope of the streets. Look at where the underpasses are. Look at where the substations sit. Look at where the data centers are. Look at where the hospitals are. Look at where the schools are. Look at where the public housing is. Every one of those decisions was based on assumptions about rainfall intensity, flood frequency, heat thresholds, wind loads, and seasonality. Those assumptions were drawn from data sets that ended at some specific year. Most older cities are operating with infrastructure that encoded the climate of the mid-20th century. Some newer construction encodes assumptions from the 1990s or 2000s. Almost none of it encodes the climate of the 2020s, because that climate is still being characterized. This is the deepest reason atmospheric anomalies translate into human disasters. The drainage system in many cities was sized for rainfall rates that occurred under a cooler atmosphere with lower moisture capacity. The same storm today, carrying more water because the air column holds more water, can overwhelm those systems even when the synoptic pattern looks familiar. The substations that power critical loads were sited under flood zone assumptions that did not anticipate either modern precipitation extremes or the long-term subsidence of certain coastal areas. The HVAC capacity of many buildings was designed for the heat regime of an earlier decade. Hospital ventilation systems were sized for emergency loads that have since been exceeded during extreme heat events. None of this is anyone's individual fault. The people who designed those systems were doing reasonable work with the data they had. The problem is that the data they had has been quietly aging out of relevance, and the cost of updating large-scale infrastructure is enormous, slow, and politically difficult. Meanwhile, the atmosphere does not care about budget cycles. This is the bathtub with the plug pulled again, cities filling faster than they drain. Not because the city is failing in any singular way, because the systems were designed under a smaller energy assumption, and the new energy is showing up in events that exceed the design. And this is where the current upper atmospheric event becomes operationally significant beyond pure science. A reorganized hemispheric flow that produces persistent regional patterns will test these design assumptions in ways that single-event analysis cannot anticipate. It is not one storm. It is the regime. The regime may produce repeated stress on the same systems, the same flood corridor, the same grid choke point, the same hospital, the same neighborhood, the same supply chain. A 2020 paper by Z. Schachler and colleagues in Nature Reviews Earth and Environment laid out the framework for compound climate events in detail. The takeaway, translated into operational language, is that the relevant analytical unit for risk in the new climate is no longer the isolated extreme. It is the sequence, the compound, the interaction. That requires a different kind of municipal thinking. It requires looking at risk not just as a probability of an event, but as a probability of an overlap between events. It requires asking what happens if heat hits during a power outage. What happens if flooding hits during a labor shortage? What happens if a winter storm hits during a respiratory virus wave? What happens if a wildfire smoke event hits during an air quality sensitive heat dome? These are not edge cases. These are the patterns the new climate is increasingly producing. And the current atmospheric configuration is a reminder that the system can hand us multiple stressors compressed into short windows, not as punishment, just as physics. The cities that begin to ask these compound questions seriously, that begin to invest accordingly, that begin to plan land use, energy, water, public health, and emergency response as coupled systems rather than separate departments, those are the cities that will fare better as the decades unfold. The ones that wait for each disaster to teach them the lesson individually will pay the tuition in lives and budgets. That is not a prediction. That is already happening. Food systems have always lived in close conversation with the atmosphere. Farmers have always read clouds, soils, frost dates, and storm patterns. Agricultural knowledge is, in many ways, the oldest weather forecasting infrastructure humans built. That knowledge is now under strain. Because the patterns that worked for centuries, locally calibrated, generationally transmitted, deeply embedded in regional cultures, were based on the assumption that next year would broadly resemble last year, and that the variability around that expectation would stay within a familiar envelope. That assumption is breaking. Planting windows are shifting. Frost dates are becoming unreliable. Pest ranges are expanding into regions whose crops did not evolve to resist them. Pollinator timing is decoupling from bloom timing in some ecosystems. Heat stress is intersecting with critical growth stages in ways that reduce yields even when total seasonal temperature and precipitation look acceptable in summary statistics. Drought patterns are persisting longer and breaking more violently. The current atmospheric event matters for agriculture, not just because of the immediate cold or warm or wet or dry impacts in the coming weeks, but because it is part of a pattern in which the calendar itself becomes less reliable as an organizing principle. That calendar is becoming unreliable. Farmers know this. Many of them have been saying so for years, quietly, in language that is more practical than political. The almanac that grandparents used is no longer fully predictive. The growing degree day accumulations are running early or late. The hail risk season has expanded or shifted. The irrigation demand has changed. The crop insurance products that were designed for one risk profile now have to cover events the actuarial tables did not contemplate. A 2019 paper by Ortiz-Bobia and colleagues in Nature Climate Change documented declining agricultural productivity growth attributable to climate change, even after accounting for technological progress. The result was striking in its calm precision. The climate has been quietly eating into the productivity gains that would otherwise have occurred, not in dramatic individual famines, in aggregate friction across global food production, and the friction compounds, because food systems are not just affected by weather at the farm level. They are affected by transportation disruptions, by storage failures during heat waves, by labor availability during extreme conditions, by water allocation politics, by export market volatility when major producers have bad years. Every link in the chain feels the atmosphere. When the atmosphere produces a hemispheric reorganization like the one we are watching now, the agricultural risk does not respect crop boundaries or political borders. A persistent blocking pattern over one breadbasket region, while another runs unusually wet or unusually dry, can ripple through global commodity markets within weeks. The disruption may be invisible at first to consumers far from the affected fields. It is rarely invisible to the people who price futures contracts and stock supermarket shelves. And here is the layer beneath the layer. Agriculture is also a major emitter of greenhouse gases and a major consumer of land and water. So the same sector that is increasingly stressed by the changing atmosphere is also entangled in the system that is forcing the change. That entanglement is not a moral problem to wave at farmers. It is a structural problem the entire civilization shares. The question of how to feed billions of people while not adding to the forcing, and while adapting to a moving climate, is one of the central practical challenges of the century. It does not get solved by social media debate. It gets solved by serious, sustained, technically literate work, much of it already underway in agronomy departments, breeding programs, soil science labs, and irrigation, engineering firms that rarely make headlines. The current event is a reminder, not a verdict. A reminder that the atmosphere is no longer a passive backdrop to agricultural planning. It is an active variable. It must be treated like one. The dice are loaded. The fields are below. Most people still think of public health and weather as separate categories. They are not. A heat wave is a public health event. A cold outbreak is a public health event. A wildfire smoke episode is a public health event. A flood is a public health event. A prolonged drought is a public health event. A pollen-altering early spring is a public health event. A vector-shifting warming season is a public health event. A power outage during extreme weather is a public health event. And as the atmosphere produces more frequent, more persistent, and more compound extremes, the public health system finds itself increasingly forecasting against the same shifting climate as everyone else, with much less infrastructure devoted to the task than is warranted. Heat is the most documented example. Heat kills more people each year in many countries than any other weather hazard. It does so quietly, without the visual drama of a storm, without the cinematic destruction of a tornado track, through cumulative stress on cardiovascular, renal, respiratory, and neurological systems, through interactions with chronic conditions, through medication-related vulnerability, through housing inequality, through occupational exposure, through the mismatch between human thermoregulation and a warming atmosphere that produces conditions where the wet bulb temperature edges toward physiological limits. A 2023 paper in Nature Medicine attributed tens of thousands of deaths during a single European summer to heat exposure during a sequence of compound heat events. The number was sobering. The mechanism was unsurprising. The atmosphere had organized into a pattern that allowed heat to accumulate, persist, and exceed the capacity of human bodies, and built environments to compensate. That is not a faraway problem. That is a forecast. Cold has its own pattern of mortality. So does air pollution from wildfire smoke. So does the spread of vector-borne disease as temperature and moisture conditions shift the ranges of ticks and mosquitoes. So does the burden on mental health that accompanies repeated disasters, chronic uncertainty, and economic displacement from extreme events. The current atmospheric event will register in health systems whether or not the systems are ready to measure it. Cold-related cardiovascular events in regions with cold intrusions. Heat-related stress in regions under unusual ridges. Respiratory consequences if any wildfire activity ignites in unusually dry zones. Mental health load in communities under repeated alerts. Strain on emergency rooms during infrastructure failures. Pharmacy disruptions during transportation shutdowns. Dialysis appointments missed when roads close. Oxygen deliveries delayed when grid stress. These are not speculative scenarios. These are the operational realities of weather-health interaction in the modern era. And the structural problem is that most health systems were not designed with the climate as a primary input. They were designed around demographics, disease prevalence, and economic geography. The climate variable was assumed to be relatively stationary. Hospitals were sited, staffed, and stocked according to those assumptions. As the atmosphere becomes a more active risk factor, those assumptions show their age. This is why some public health agencies have begun building dedicated climate health programs. It is why the World Health Organization has pushed climate and health onto the agendas of national ministries. It is why insurance models, building codes, and labor protections are increasingly being asked to incorporate climate stress. It is, again, slower than the atmosphere. And so the gap shows up where the gap always shows up. In emergency room wait times, in rural ambulance availability, in nursing home cooling capacity, in low-income housing weatherization, in urban heat island measurement, in wildfire smoke filtration access, in the chronic, grinding burden on the people who keep these systems running while the climate keeps moving. The atmosphere is no longer just outside the hospital window. It is in the triage flow. If there is one infrastructure category that sits at the absolute front line of the new climate, it is the electric grid. Power systems are weather machines. They generate using technologies that depend on water availability, fuel logistics, wind patterns, and solar irradiance. They transmit through infrastructure exposed directly to wind, ice, fire, and flood. They distribute through equipment that has thermal tolerances and mechanical fatigue limits. They serve loads that are increasingly weather-sensitive because of the rise of electrified heating, cooling, transportation, and industrial process demand. Every weather extreme is also a grid event. A heat wave drives air conditioning demand at the same time. It reduces the efficiency of thermal generation, increases transmission line sag, and lowers solar panel performance per unit irradiance because panels overheat. A cold outbreak drives heating demand while potentially freezing gas supply chains, icing wind turbine blades, and stressing equipment that was not winterized for extreme conditions. A wildfire risk episode can force precautionary shutoffs of transmission lines. A flood event can submerge substations. A windstorm can topple distribution poles by the thousands. The grid is the most exposed engineered system in modern civilization, and the current atmospheric event is, in its own way, a grid event already, even before the surface impacts are fully resolved. Because operators do not wait for the weather to land before adjusting their posture, they preposition crews. They model peak load scenarios. They review fuel inventories. They communicate with neighboring balancing authorities. They prepare for the version of the forecast they cannot afford to be wrong about. And in a regime where the upper atmospheric state suggests persistent, amplified flow, the grid has to plan not for one bad day, but for a sequence of stressful days that may last weeks. That is a different operational posture. It is also a different financial posture. Fuel costs can spike, wholesale prices can swing, emergency reserves can be depleted. Demand response programs can be activated. Customers can be asked to conserve. If the pattern locks in, the cumulative stress on the grid can begin to exceed what individual peak day planning was designed to handle. This is where the recovery gap shows up in megawatts. Crews are still repairing one storm's damage when the next event arrives. Inventory of replacement transformers is drawn down. Mutual aid agreements between utilities, which depend on neighboring systems being able to spare resources, become harder to fulfill when many systems are stressed at once. A 2021 analysis of the Texas February freeze documented exactly this kind of cascade. The atmospheric event was severe, but not unprecedented in pure meteorological terms. The disaster was created by the collision of the meteorology with an energy system that had not been winterized to handle the duration and intensity of the cold. Combined with gas supply infrastructure that froze, combined with regulatory frameworks that had not required the level of resilience that the event demanded. Hundreds of people died. The economic damage ran into the tens of billions. That event was a warning, not a one-off. It was a demonstration of what happens when the atmosphere reaches a configuration that exceeds the planning envelope of a critical system in a populous region. The current upper atmospheric anomaly raises the probability, not the certainty, the probability, of similar configurations reaching into multiple regions over the coming weeks. And the energy systems exposed to those regions are now being tested against atmospheric states that, in some cases, have not been part of their formal stress testing scenarios at all. This is what it means for the grid to live downstream of the stratosphere. It is not a hypothetical statement. It is a description of how operational reality now works. The window is closing in places where the window was already narrow. After all of this, the stratosphere, the ocean, the jet stream, the cities, the crops, the hospitals, the grid, the final layer is the one most easily lost in the technical discussion, the human layer. Every atmospheric anomaly resolves, eventually, into individual lives. A grandmother who could not get to a cooling center, a farmer who watched a crop fail at the wrong week, a child whose school closed for the fourth time in a month, a nurse who worked a double shift because two coworkers could not reach the hospital, a father who lost a roof, a daughter who lost a parent, a neighborhood whose memory of safety is no longer reliable. These are not abstractions. They are the actual unit in which weather is felt. And the deepest reason this current event matters is not the chart anomaly. It is the cumulative pressure that increasingly unusual atmospheric behavior places on lives that were built for a quieter climate. Resilience is not infinite. People are not infinite. Communities are not infinite. The repeated experience of disaster, of warning, of recovery, of partial restoration, of new warning, of new recovery, takes a toll that is not always measurable in dollars or statistics. It shows up in mental health. It shows up in migration patterns. It shows up in slow demographic shifts away from places that were once stable. It shows up in the quiet decisions people make about whether to invest in a home, a business, a community, a future. Climate is becoming, for many people, a backdrop of chronic uncertainty against which life decisions must now be made. That is a profound social change, and it is happening even in places where the headline disasters have not yet arrived. because awareness is itself a kind of exposure. Knowing that the atmosphere has moved into states humans alive have not seen is itself information that changes how the future is imagined. There is no clean way to package this part of the story. There is no neat ending. There is no consoling sentence that says it will all work out, because honest analysis cannot make that promise. The atmosphere is going to keep doing what physics requires it to do under the conditions humans have, collectively and over generations, created. What is left is the choice of how to respond. And response is not a single act. It is a long discipline. It is mitigation through emissions policy and energy transformation. It is adaptation through infrastructure investment, public health preparedness, urban redesign, agricultural innovation, water management, ecosystem stewardship. It is communication through honest, technically literate, emotionally steady information work. It is community through the slow building of networks that can hold together under repeated stress. None of those are flashy. None of them fit on a thumbnail. None of them feel as satisfying as a single dramatic intervention. They are the unglamorous, unending, deeply necessary work of living inside an atmosphere whose operating envelope has widened. And the people doing that work, the meteorologists, the engineers, the public health officers, the emergency managers, the grid operators, the farmers, the urban planners, the climate scientists, the public communicators, the parents, the neighbors, the volunteers, are doing it now, every day with or without recognition. The current atmospheric event is, for them, another chapter in a long story they have been living for some time already. What is changing is that the chapters are coming faster, and the public is increasingly being asked to read along. So you have stayed with me through all of this, through the stratosphere, through the jet stream, through the ocean heat content, through the conspiracy debunk, through the infrastructure, through the health systems, through the grid, through the human layer. What do you actually do with it? First, you stop treating each anomaly as an isolated curiosity. You start understanding that the events you are reading about are connected through a single coupled system that is in active reorganization. That mental shift alone changes how you interpret news, how you make decisions, how you talk to family and neighbors. Second, you take preparedness seriously without descending into panic. Basic emergency supplies, a communication plan, knowledge of where local cooling and warming centers are, awareness of which neighbors might need help. Insurance documentation kept where it can be reached, medications stocked with appropriate buffers. These are not extreme measures. They are reasonable adaptations to a world where compound events are more likely and recovery windows are shorter. Third, you push the systems around you to take this seriously too. Building codes, utility planning, school emergency procedures, workplace heat protections, urban tree canopies, floodplain management, agricultural extension services. These do not change because individuals shrug. They change because individuals, communities, professionals, and policymakers refuse to keep designing for a climate that no longer fully exists. Fourth, you treat information itself as part of your preparedness. Identify trustworthy sources, verify before you share, distinguish observation from speculation. Recognize the limits of forecasts and respect the careful language of uncertainty. Push back calmly on misinformation when you encounter it. Not by mocking the people who repeat it, but by offering the more accurate explanation patiently. Fifth, you stay engaged after the headlines fade. Recovery is where most of the long work happens. Months and years after a disaster, the same communities are still rebuilding, often with diminished attention from the outside world. That is when sustained support, financial, civic, political, matters most. Sixth, and this is the hardest one, you make peace with the open loop. You accept that some questions about this event will not be answerable for years, that some forecasts will not verify cleanly, that the science will continue to refine itself as the data accumulates, that the right answer to "is this climate change?" is often "this is consistent with what a warming climate makes more likely," and the precise attribution will be quantified in due course. The honest stance is not certainty, it is calibrated attention. That is what living inside a changing atmosphere requires. Part 30. The atmosphere will not announce when it is done. We have reached the end of what I can tell you with reasonable confidence about the present moment. The stratospheric anomaly is real. The downward coupling is in progress. The ensemble guidance is showing a wider spread than usual. The oceans below are warm. The land surfaces are primed. The infrastructure is calibrated to assumptions that are aging. The information environment is noisy. The public language is straining. The institutions are responding, some faster, some slower. The atmosphere is still moving. What I cannot tell you is exactly what comes next, not because I am being cautious, because the system itself has entered a region where caution is the only honest posture. The pattern may resolve in ways that, in hindsight, look less dramatic than the most aggressive scenarios. It may resolve in ways that look more dramatic. It may resolve in ways that surprise everyone, including the people whose entire professional lives have been devoted to this exact question. That is what it means to forecast through the edge of the known envelope. But here is what is not uncertain. The fact that the atmosphere produced this state at all is information. The fact that the operational analog catalog cannot match it is information. The fact that the ensemble systems are struggling is information. The fact that the ocean is at record heat content underneath this entire event is information. The fact that the Arctic continues to evolve under the upper air anomaly is information. The fact that the public conversation around it is fragmenting along familiar lines is information. All of that information points in the same direction. We are living inside a system that has more energy, more variability, and more capacity to surprise than the institutions designed to manage it currently account for. That is not a prediction of doom. That is an observation of state, and from that state, two paths exist. One is denial, the path that treats every new anomaly as a fluke, every warning as exaggeration, every adaptation as wasted money, every mitigation effort as unnecessary. That path is comfortable in the short term and ruinously expensive in the long term because the atmosphere does not care about comfort. The other path is engagement. It is harder. It requires that individuals, communities, businesses, and governments treat the new climate as a real, present, ongoing challenge that demands sustained, technically literate, emotionally steady response across multiple domains for the rest of our lives and beyond. That path is uncomfortable in the short term and far less ruinous in the long term because it works with the physics instead of pretending the physics is optional. There is no third path. There is no waiting for clarity. There is no expectation that the atmosphere will pause until society catches up. So the question is not whether the current event will resolve cleanly. The question is what we learn from it, what we change because of it, what we refuse to keep pretending after it, because the atmosphere does not announce when it is done. It does not send a notice that the disruption is over. It does not return to a clearly labeled previous state. It moves on to the next configuration, and the next, leaving behind a record that researchers will study for decades and citizens will live through whether they pay attention or not. The only choice is whether to be a passenger or a participant in that record. Right now, today, in the present tense, the atmosphere has shown us something nobody alive has ever seen. The honest response is not to look away. The honest response is to look harder, to learn more, to ask better questions, and to refuse the false comfort of a story too small to fit the system we actually live inside. The atmosphere just did something nobody alive has ever seen. It is far from over. It will not be over for the rest of our lives. And that is not despair. That is the beginning of an adult relationship with the planet we have. The forecasts will continue. The events will continue. The recoveries will continue. The science will continue. The arguments will continue. The work will continue. So will we, if we choose to.